So, welcome to the third lecture of the NITheCS SATACS course on category theory. Today we're going to look at the concept of composite of morphisms in a category. So, suppose we have a path of morphisms. Let's say this is object x0, and we have morphism f1, and then here we have object x1 and a morphism f2, and it goes on until some morphism fn leading us to object xn. One of the axioms of a category says that any path can be reduced to a single morphism in the sense that there is a morphism joining the starting point of the path, the object x0, with the end of the path, object xn. Let's call that morphism f, such that the morphism f, seen as a single morphism path, is equivalent to our original path. So we have the equivalence of f and the path f1 up to fn, which I'm going to write with brackets enclosing the sequence to make the notation more clear. So this must exist for every path, such f, and that's our axiom of reduction. But then we also have another axiom saying that if two single morphisms, seen as single morphism paths, if they are equivalent to each other, then they will also be equal to each other. So that means the following. Imagine I had another candidate, another f prime, let's say, that is also equivalent to the given path. So f prime that's equivalent to the path f1 up to fn. Can I conclude from this that f is equal to f prime? Would anybody like to tell me if they think I can make such a conclusion based on the axioms of a category? So let me repeat the question for you. I've got a path joining x0 and xn, path of f1 up to fn, and I have a morphism f that's equivalent to it, which I know exists by the reduction axiom. But now I also have, let's say, another morphism f prime that's also equivalent to the path. When I say a morphism equivalent to the path, I'm regarding a morphism as a path itself, a path having just one morphism in it. But now the question I'm asking is whether the fact that the morphisms f and f prime are both equivalent to the same path, whether that implies that f and f prime are actually equal to each other. Remember that if they were equivalent to each other, they would be equal by the axiom of equality. But in this case, we're not saying they're equivalent to each other, we're saying they're equivalent to the same third path. Thanks, Brendan, for the suggestion there. We do have transitivity of equivalence as one of our axioms of a category. I think it was the third axiom. And so we could say then that because f is equivalent to that path, and that path itself is equivalent to f. So f prime is equivalent to that path, right? And that path is equivalent to f. Then from this we can conclude that f prime is equivalent to f, and from that, by axiom of equality, we can conclude that f prime actually equals f. But this means that for every path, we always have exactly one morphism f to which the path is equivalent. So we can see this as a sort of construction, a process of constructing a single morphism out of a path of morphisms, which always yields unique answer for the same path. So it will be useful to have notation for that. And the notation for that unique f is the following. We write the unique f morphism from x0 to xn, which is equivalent to the given path f1 up to fn. We write it as this. And we call it the composite of these morphisms. And we call it the composite of, well, of the path. So the circle thing here is, of course, a familiar notation. We use it for composing functions. And indeed, that will be one of our examples where in the category of sets, where morphisms are functions between sets, these composites we're defining here will match with the usual way of composing functions. There is an interesting special case of this construction. And this is the case when n equals 0. When n equals 0, but what happens when n equals 0? When n equals 0, x0 ends up being the same as xn, right? If n is 0, x0 is the same as xn. And then there are no way of fitting morphisms between these, because every time I show a morphism, I need to go to the next object on my diagram. So when n is 0, we don't have any morphisms in the path. We call it the empty path. So in the case when n is 0, the sequence f1 up to fn just becomes an empty sequence. But it's still a path from the fixed objects, the objects we fixed at the beginning. So it is an empty path from x0 to x0, because now n is equal to 0, right? And the composite of this empty path is a very important thing. And it's written the following way. We write the composite of this path, in other words, of the empty path from x0, let me just say x now, from x to x, as one subscript x, and call it the identity morphism of the object x. We began these lectures by describing morphisms as processes that take place between objects. And so we can think of the empty path as a process of nothing happening. If you remember the example we had with the train lines between cities, the empty path would be that I'm standing on the train station. I'm not going anywhere. I'm staying there. But in a category, every path needs to have a realization as a morphism. So even the empty path can now be described by a morphism. And that morphism that describes the process of doing nothing is called the identity morphism. It's written like this. Does anyone have any questions so far on these two concepts? The concept of a composite of a path, and then the special case of it, the concept of an identity morphism. Are there any questions so far? So does everybody understand these the concepts? Do you feel that you understand them well? I've got one thumbs up on the list of participants there. Okay. Second one is up. Seems like it's all good. Okay, great. What we're going to do now is to look at a very important example of a category that can illustrate for us this process of composing morphisms in a path. We can call this the category of matrices. So it's a category that's very important to linear algebra. And as such, it's also very important to various applications of linear algebra, such as, for instance, in physics, quantum computing, and even in AI, where linear algebra is a basis for these systems like ChatGPT and others. The category of matrices. When we learn about matrices for the first time, and I suppose all of you have encountered matrices before, there is something weird about matrices. Unlike numbers, where every two numbers can be multiplied with each other, it is no longer true that any two matrices can be multiplied with each other, right? Let's actually remind ourselves how the matrix multiplication works. So if I have n by I'm just trying to see what is the best notation here. Let's say I have an m by n matrix given by entries a, I, j. So this short notation refers to an arrangement of entries where my number of rows in the matrix is n, and the m, and the number of columns is m. So n is the number of rows, and the number of columns is m. And the first subscript refers to the row. So this would be A11, then A12, and so on. It goes all the way up to A1n. And then here it goes all the way down to AM1. The other one goes all the way down to AM2. And finally, the last entry in the corner there is AMN. So let's say I've got a matrix like that, and then let's say I have another matrix like that with possibly different dimensions. So the dimensions of the second matrix could be, let's call the second matrix B. So A is the overall matrix there. And let's say the dimensions of B are, instead of M and N, let's say they are R and S. So one thing that's sort of weird about matrices is that we cannot just take any two matrices and multiply them, right? I cannot consider B times A unless something happens. When is it that I can consider B times A? When can I multiply two matrices? When can I multiply a matrix, an R by S matrix with an M by N matrix?
S equals M?
Yeah.
That's right, yeah. So there are actually two ways of doing this, and the traditional way of doing this is to consider when S is equal to M. So let's do that. Let's change our S to M. And can we all write the general entry of the matrix? So the resulting matrix will be an R by N matrix. This coordinate here, this dimension here somehow gets cancelled with the other one. Just to it's always useful to think of this visually. So if I've got my B matrix and I've got my A matrix, I will be designing the terms by multiplying the rows and the columns in the following way. So I take an individual entry in the row, and I multiply with so I take first entry, multiply with the first entry, then I take second entry, multiply with the second entry, and so on. And then eventually I add all of these products, right? Then I take a sum. And as you can see, so the value I get will be an entry in the new matrix at a certain position, and the position of that will be determined by the position of the row and the position of the column. So let's say the position of the row was I, and let's say the position of the column was J. Then this thing that we described will have position at ith row and jth column. So this is the ith row, and this is the jth column. We can then write down the formula for the entry here as a sum, where we take B I let's say K, and we multiply each BIK with A K J, where we let K run from 1 to M, so that you see the sum will not depend on K anymore, because K is the one that we have under summation. So it will be adding all of these terms up, but it will still depend on I and J, and this will give me the ijth entry here. So that actually this value here is the thing we have right there. Let me rather use purple color. That's the thing we have right there. Is it still good so far? Any questions? So this mystery of the fact that not any two matrices can be multiplied, in fact, is not a mystery at all, in the sense that, in fact, there is an underlying category where the matrices that can be multiplied with each other are exactly those morphisms that form a path in the category. So we're going to be setting up that category now. The objects of the category are going to be dimensions of matrices. So they are these things we put here. And they are numbers. Which kind of numbers are they? So number 2 is there. We can have dimension to be 2, 3, 4, right? But we can also have 1. And furthermore, we can even have 0. And maybe that 0, exactly, Joseph, so these are all the natural numbers. Maybe for some of you that 0 might be a bit surprising there, because what would you do if this M or N is 0, what kind of matrix will we get as a result? But we'll come back to this question in a moment. So objects are the natural numbers, and morphisms, they are matrices. So a morphism from N to M. So since objects are natural numbers, now I can write them down as N and M as usual, but I write natural numbers with these letters. And a morphism from N to M is an M by N matrix. Okay, so I've described what objects are, and I've described what morphisms are. So now I need to describe what equivalences are. I need to describe when are two paths equivalent to each other, right? Any questions so far? So let's consider two paths. So this time, well, previously we were calling these objects that we encounter along the path, we were calling them x0, x1, and so on. Now we should probably call them n0, n1, and so on. But we'll have two of them. So let's first fix n and m, and then consider different letters, maybe A0, A1, A2, going all the way up to some U, which is equal to M. And then another path, let's call the objects in the other path B0, B1, B2, going all the way up to, let's say, BV. That's also equal to M. And then here we have morphisms, which are our matrices in this case. So it's we've got some matrix, let's say A1 and A2 and A3, and it goes all the way to AU. And then we have matrix B1, B2, B3, and it goes all the way up to BV. Now we need to describe what do we mean in this context. What do we mean for two paths of morphisms to be equivalent? And of course, this is completely up to us. We can say whatever we want to. Whatever we say will give us some kind of sketch, right? But we want to say something that will be actually useful for linear algebra. And so we're going to define this to mean. So this means these two paths are equivalent to each other if and only if the product of the matrices AN all the way down to A1 is equal to the product of the matrices B, sorry, this is not AN, this is AU. AU multiplied all the way down to A1, that is equal to BV multiplied all the way down to B1. But can these matrices even multiply? Because we know that not every two matrices can be multiplied, right? Well, if, for instance, I look at A2, A2 is an A2 times A2 by A1 matrix, right? And if I look at A1, that's A1 by A0 matrix, and so A2 and A1 do multiply indeed, because you see the dimensions exactly match the way they should. The dimension that gets annihilated is this one, right? So maybe that's something I should have said already earlier here when I described the morphisms. This requirement for this dimension to match with this one, this requirement is precisely the requirement of the two morphisms forming a path. So according to this definition of a morphism, we are viewing for instance, in this case of A and B, we are viewing A as a morphism from N to M, so that's A, and the B we are viewing as a morphism from M to R. And you see, the fact that they form a path is precisely the fact that this first number here matches with the second number there. That's exactly what enables us multiplication of matrices. And so this will be true for any consecutive matrices on the path. And so we can multiply all of them as well. And then we define equivalence of paths by requiring that these products of matrices are equal to each other. Now, in this example of a category, and well, first of all, we have to prove that it's a category, right? Maybe we should quickly see why will this be a category. But before we see that, if we just go back to our first part of the lecture, which was this idea of composite of morphisms in a path, what do you think will be the composite of these morphisms? Which matrix? Well, it has to be a matrix from n to m, right? So what do you think will be the composite of? So it has to be a single morphism that's equivalent to that path. And so what do you think it will be?
It's going to be an n times m matrix.
Yeah, but which well, it actually will be m by n matrix, but the question is which m by n matrix will it be? So to come back to that question, let me copy paste this here. So remember that the composite is defined by I mean, a composite is a single morphism that's equivalent to the long one, right? To the path, right? So now here, if in this definition of equivalence of paths, if I take my B path to consist of just a single morphism, so I'm going to modify this picture by replacing my B path with just a single morphism. So it will be a single morphism path. And I'm going to call this thing B1. So there is only one term in the sequence of the B matrices. What will happen to this equivalence? Well, here I'm just going to have B1. I'm not going to have the other B's, right? So they can be removed. And so then I get the answer to my question, right? B1 is a composite of the A's precisely when B1 is the matrix product of the A's. So we see that in the category of matrices, composition, this process of forming composites, composition corresponds to, composition becomes matrix multiplication. So in a general category, we had this process of taking a path of morphisms and forming a single morphism that's equivalent to it. In the category of matrices, the single morphism can be computed to be the product of those matrices. Anybody wants to ask a question here, if anything is unclear?
So in a way, the composition that takes a specific nature depending on the category.
You got it absolutely right there. That's exactly what's happening.
Okay. It just happens that in function, the composition becomes the composition of functions, but here it's going to be the matrix multiplication in this example.
Absolutely, absolutely. That's exactly what's happening. Now, let us go into the special case when the paths are zero, so or where the dimension is zero. So because this is something that is not typically discussed in a linear algebra course, but we need it here, and so let's clarify what's going on in that case. So what should be rather, because we might not have defined it before, what should be a 0 by n matrix? So previously we wrote matrices like this, right? The dimension was in the corner there in the subscript. And in the square brackets, we would write the general term of the things that occur inside the matrix. So for us, this is now a morphism. And the question is, what should go in here? Any ideas? So this must be a matrix having 0 many rows, yeah, and n many columns. Joseph says that 0 must go in there.
Well,
Now, Joseph, yeah, Alexander?
I think it should be literally nothing, because it's like no rows, not one.
Yeah, exactly. So if we put a 0 there, it means that there is at least 1 row and at least 1 column. But here we have 0 many rows, so that we cannot put anything there. It's like an empty box. So if we think of a matrix as a box with compartments, we can really think of a matrix like that, right? We can think of a matrix as a box with compartments. Let's say this is a 3 by 4 matrix. Sorry, yeah, 3 by 4 matrix. And we can think of it as a box with compartments, and then inside those compartments, we've got some numbers in each compartment, right? So this has 3 rows and 4 columns. But if we now require that the number of rows is 0, it means that we cannot have any row of compartments. So the box will have no compartments. It will just be if we place our box of compartments on a tray, then the matrix with 0 rows will just be the empty tray with no box on it, with nothing on it. So this tray serves the role of these square brackets. Now, there is a problem that arises here. When I have an actual box with actual rows and columns, I can tell the dimension of my matrix just by counting how many rows I have and counting how many columns I have. Here, when I have empty tray, I can no longer see how many rows and columns I have. One of them I know is 0, but the other number I don't know what it is, right? So I could tell that one of them is 0, but I don't know which one, and then even if I knew which one, then I don't know what the other number was. And that's why also this notation, when we write the dimension as a subscript, is useful, because now the entries of my matrix no longer tell me what the dimension is. So it's useful to keep track of what the intended dimension should have been. Okay, now that we learned about empty matrices, let's see how we can multiply them. So there are 2 different ways of multiplying them, right? We could take an empty matrix like this and multiply it with another matrix, but now this other matrix will have to come out from where A went into, right, to form a path. And so the other one will also end up being an empty matrix. So this is one way we can compose an empty matrix with something. The other way is the other way around. So the other way would be if I try to put my A here and try to multiply on the left with something that maybe goes out from K. So some C matrix that's an n by K matrix. So there are these 2 ways I can combine the empty matrix with others, and let's see in each case what are we going to get.
Why in the first one we are multiplying empty matrix, we seem to get something that is not empty?
Sorry, say that again.
On the first one, we are multiplying 2 A and B. These are empty matrices, but their composite is not empty, isn't it?
Yes, that's the magic. That's the magic we're building up to. How to get something out of nothing. if you have an empty linear combination of vectors in a vector space, you get the vector 0. This is why we say that a vector space which only has the 0 vector has dimension 0, because your basis can be empty. So that's another example of getting something out of nothing. Take nothing and form the set of nothing. You will get something. It will be the empty set. So again, an example of getting something out of nothing. And here we have another phenomenon. We've got two empty matrices. We will multiply them and we will see that we will get an n by n matrix. But now let's see which n by n matrix will this be. So according to the formula, B times A must be a matrix whose entries are the summations of BIK, AKJ, where K runs from where to where?
0 to 0. 1 to 0, I mean.
Yeah, from 1 to 0. Yeah, because I think we started our indexing with 1. There we go. K was from 1 to, I forgot to put here, by the way, here K was from 1 to M. And so here K is from 1 to 0. But of course, K cannot run up from 1 to 0. So actually, this means that there are no summons in the sum, right? It's the sum of nothing. What is sum of nothing?
It's nothing.
It's not, well, but we have a number for measuring that quantity. It's number 0.
Oh, yeah.
If I have 3 people in the room and I'm a very evil person, I go to the room and I collect from each person some gold coins. Maybe these are people with gold coins in their pockets, and I'm an evil person, I want to rob them. I go to the room, I collect from each of them certain number of gold coins. I walk out of the room, I will have certain number of gold coins, right? Now, once I went into a room and I found nobody there. And so me as a thief will walk out from the room with, I always walk out from the room with certain number of gold coins, but in this case, when I find nobody there, of course, I will walk out with 0 many gold coins. So each person in this analogy represents a summon. If I have 2 summons, whatever this contributes, whatever that contributes, their sum is the total of these contributions, right? But if I have no summons, there is still a total contribution, which is 0. So this will be an n by n matrix where every entry is 0. So it will be the 0 matrix. Now let's look at the other one. When I multiply the empty matrix with a non-empty matrix. So here the formula will be again sum AIK CKJ, where K again goes from 1 to 0. No, sorry, the K doesn't go from 1 to 0 anymore, does it?
Goes to N.
Yeah, it goes from 1 to N. And the dimensions of this will be 0 times K. Well, if the dimension is 0 times K, then it's the empty matrix, right? There is also another form of empty matrix, the one that is a morphism from 0 to N. This is also empty matrix. In this case, in the previous case, it was the rows that we didn't have. In this case, it's the columns that we don't have. And similar laws will hold here. So if I have a situation like this, the product will be empty matrix. It will be the one going from 0 to K. And if I have a situation like before, then the B plays the role of my D, right? So these are kind of the 3 different cases to consider here of multiplying empty matrices of 2 different kinds with all the others. And in this last case, again, we end up with an empty matrix with dimension, this time k by 0. Any questions on this? Everything is clear to everybody? Everybody happy with where we are so far? Great. I see Brandon is happy. What about others? Okay. It seems like, well, not everybody is giving their thumbs up, but I assume that if somebody is not happy while many of you are saying you're happy, I assume that you will say that you're not happy, and not to force everybody to always necessarily click that button there. Okay, so we can now go on and check that we actually get a category. So let's very quickly revise what the axioms are and how we're going to check them. The first one was reflexivity. Any path is equivalent to itself, and now that of course would mean that the product of matrices is equal to itself, and so that will kind of trivially be true. Let me bring back this picture to make it absolutely obvious what we're talking about here. So for E1, we want to check that when these B's are also the A's, right? So when first of all U equals V and each B I equals AI, in that case, the equivalence will be saying that AU times A1 all the way to A1 is equal to AU times all the way to A1, right? And this is certainly true. The product of matrices is certainly equal to itself. So reflexivity holds. Symmetry says that if one path is equivalent to another one, then the other way also should be true. So in the language of matrices, this will mean that if this holds, then the other way also should hold, which means that the product of the B's must be equal to the product of the A's. And that, of course, is certainly true. We can always swap the order of equality. Transitivity is similarly easy, right? If one product is equal another product and the second product is equal to the third product, then the first product will be equal to the third one. So for E3, we will have a diagram where we have also a third thing here, C0, C1, small c1, then capital C2, small c2, going all the way to some CW, which is equal to M. And so we are given that these two are equivalent to each other. So in other words, we're given that the product of the A's is equal to the product of the B's, but we're also given that the product of the B's is equal to the product of the C's. And from this, we should be able to infer. So the question is whether this implies or not that the product of the A's is equal to the product of the C's, and of course it does. So that would mean the product of the A's being equal to the product of the C's would mean that this path is equivalent to this one, which is exactly what transitivity tries to achieve. So transitivity is sorted. Then we have the congruence axiom. So This is maybe slightly more interesting than the others, maybe slightly less trivial, although this will also be quite easy to establish. So if you remember these axioms very, very well, then this is probably a bit boring what we're doing now. But partly the purpose of me doing what I'm doing now is to remind you what the axioms are in case you don't remember them exactly so well. So now in the congruence axiom, we start with some two paths that are equivalent to each other, like here, and we then extend this picture with further paths. So let's call these matrices something. Maybe we'll call them D1 up to DR and C1 up to CS. And we want to infer from this, so from this equivalence, the middle equivalence, we want to infer that these longer paths are also equivalent, right? And so what would this be in terms of the matrices? So our assumption that these two are equivalent will be written out as AU times all the way to A1 being equal to BV times all the way to B1. And so how should I write down the fact that this path is equivalent to this one? What should I put here? Any suggestions? Alexandra, you want to say something?
Well, we can just multiply by matrix our both sides, no?
Yeah. So the top path will now be CS up to C1 and then continuing multiplication with AU up to A1 and then continuing with DR up to D1. And that, of course, will be equal to the same thing with B's in the place of A's. And the reason why they're equal is that the middle parts are equal. And of course, in a product of matrices, if middle parts are equal, then the whole thing will also be equal. Which, by the way, if we really want to prove this computationally using the formula of multiplication of matrices, this is not a one-line proof. You will have to really compute these things and prove these things. You first have to establish that multiplication of matrices is associative before this becomes a bit easier. So because this is equal to that, which is what the assumption says, since on these sides I have identical things, and on those sides identical things as well, the overall product will be equal to that overall product. So E4 holds. And now let's look at the last two axioms. I think I might have changed the order in my notes. So E5 is the reduction axiom. And according to this, I think we already kind of established E5. One of the first things we remarked when we defined this sketch of matrices, which now will be a category of matrices because we're proving it, this sketch is a category. So what we want for E5 is the reduction, right? Everything should have, every path should have a single morphism path that's equivalent to it. And of course, we take that to be the product of these matrices on the path. That's what we call composite of the morphisms in the path, right? So E5 holds because these are equivalent to each other. And finally, E6. And remember that E6 states that if two paths, both of which have only one morphism in it, if they're equivalent, then these morphisms must be equal. So in this case, it means that this whole series of matrices is just, in each case, is just a single matrix. So some A and some B. And if they're equivalent, by definition of equivalence, remember equivalence says that in a path I need to multiply everything, and that needs to equal to what I get by multiplying everything in the second path. But if I only have one thing to multiply, then it will be just that being equal to the other ones. And so by definition, this is the same as A being equal to B. But on the other hand, E6 was claiming that if two things are equivalent, they must be equal. But actually they are by the definition of equivalence in this example. So this holds as well. Now, the category of matrices is a very important computational tool. But behind this category, there is another category that actually is quite similar to this one, but slightly different from it, which is the category of vector spaces. So in the category of matrices, we can think of every object in terms of the dimension of a vector space. So we can think of, let's say, n to be an n-dimensional vector space. So this would be r to the power n, right? And we can think of M as an m-dimensional vector space. And those of you who are doing linear algebra, maybe this comes a bit later, maybe in the second year, not the first year, at some point you will prove that if you have n-dimensional vector space and you have m-dimensional vector space, then you can represent any linear map between these vector spaces using a matrix. And this representation is a nice representation. It's a one-to-one correspondence there. So eventually, what we're actually proving in that linear algebra course, and it's kind of fundamental result of the course, is that the category of matrices is what in category theory is called equivalent to the category of vector spaces. But today we're not going to discuss the category of vector spaces. Instead, I would like us to consider another category that is also about spaces, but not necessarily about linear algebra. I want to show you something from topology. But before we do that, I would like you to ask any questions you might have about the category of matrices. So we really exhausted everything we could have said about the category of matrices. We defined the objects, we defined the morphisms, we defined the equivalences, we proved it is a category, and we also learned that, in fact, this category has some strange matrices, the empty matrices, and we learn how to multiply them. And sometimes we saw that when I multiply empty matrices, I get a matrix that is not empty, but all the entries are zero. Any questions you might have about matrices before we move on to a different topic? Great. Seems like we can move on. Okay, so many of you probably do not know yet what, but many of you probably do know what a topological space is. We're not going to work with topological spaces in today's lecture using its formal definition. We're going to rather have an intuitive way of thinking about topological spaces. Let me start with some examples. So take our three-dimensional space, R cubed. That is one example of a topological space. What makes it topological is the idea that there is some sort of notion of continuity inside the space. For instance, if I have 2 points in the space, I can speak of a line that connects them that never breaks, a continuous path from one point to another one. And so basically you can think of a topological space as a concept that captures the idea of continuity, that I'm able to talk about things that are continuous. Let's look at another example of a topological space, a sphere. And let's only consider the surface of the sphere. So we only look at the surface. We don't look at the inside part of the sphere, just the surface. So that will be topological space, because there also we have the notion of continuity. If I take 2 points, I can have a continuous way of transforming one point into the other on the surface, right? A kind of walk on the surface. This is of course very relevant because Earth is almost a surface, a sphere, and so these paths of continuous paths will be a way of transporting from one position to another on Earth. Another example is, let me actually, yeah, okay, wait, well, so let's call it the surface of the sphere. Would some of you like to give me suggestions for another example of a topological space? So think of something in which we still have this notion of being able to move continuously from one point to another.
Well, maybe a trefoil knot.
Yes. So you could put a good challenge for me here to draw.
I know.
Okay. I think so far I'm doing good, right? But now this has to wait. This is wrong, right? It's like this, right? But there's something to be corrected here. Am I right, Alexander, or am I misremembering completely what a trefoil knot is? Let me see. Is it like this?
Well, I think it's a different knot, but it's fine.
Which one is the trefoil knot? I don't remember, apparently.
Oh, well, it's the simplest one. So like this.
Oh, you can draw on my screen. That's fantastic. Wait, what's going on in the center there?
Wait.
Can you make it precise? What's happening inside the center? Oh, but wait a second. Oh, is that different thing? Oh yeah, mine has. You've got 3. It's a triangle, and mine is hexagon, right? No, pentagon. Okay. Yeah, that's why it's called trefoil, because of 3.
Yeah.
Mm-hmm. But that picture that you posted on the chat, maybe that's even nicer than just having it as a single curve. So let me try to copy that picture. There is a helicopter at my place. I don't know if you can hear it. That's trying to make some continuous paths in the sky. So this goes like this. Okay, I made it less pretty than it was on the picture, but I think I captured the geometry right. There we go. So there are 2 different ways we can view this. One is a kind of a cylinder together with its interior that's twisted the way that it's shown in the picture. So at each point here, we could have possibly, if we cut it, we'll get a round surface. But also it could have just been a wire, a very thin, infinitely thin wire. So now let's talk about continuity in a space like this. So if I have a point, let's say here, and a point there, I can arrive continuously from one point to another, let's say by following this path, right? Then there are many other interesting examples. Klein bottle. I'm going to skip this Sierpinski space because it's a bit less natural. from the perspective I'm talking about, but the client bottle, we can give it a try. So this is called the trefoil, right? How do we spell trefoil, Alexander?
Well, just like this.
Like this. Okay, fantastic. And what is client bottle? So basically, you take a cylinder, and then you want to stick this with that, but not in the way that you get a torus, but somehow the other way. So you get a picture of the sort. Usually people also try to draw it as in the shape of a bottle. Now, what happens here is that this seems to cross the surface of the bigger bottle, the bigger section of the bottle, but actually doesn't. So this happens in the fourth dimension somehow, and it goes here, and there is this hole here. So if you think of this as a bottle, if you put water in this bottle, right? If you can pour water in here by channeling some water there. The water will go all the way up, and it will go down here, and it will fill some area here inside the bottle, but there is no hole for the water to escape, because actually what happens inside is that there is actually something like this going on. So inside the bottle, if I looked inside the bottle, if I let's say cut it here, I would see something like this. Okay, and so this is where the water would have accumulated here. So because of this boundary here, the water wouldn't have escaped. So this is called the Klein bottle. This is the name is after a mathematician, Klein, who considered this space. And once again, we have a notion of continuity here. I could begin somewhere here on the bottle surface, and maybe so we have to decide whether we're considering surface or not, and let's just consider the surface. And so for instance, moving from here to there, I will have I can have a continuous line like that. Okay, so these things, these things that are called spaces, they will be objects of our category. The morphisms will be transformations of spaces. So you take one space and you somehow continuously transform it or deform it sometimes into another one. And here is an example of such transformation. So these will be objects of our category. These will be objects of a category of spaces we are about to describe. So let's take a donut. It's a typical example topologists like to give. So let's take a donut, right? Let's only consider the surface of the donut, but we could also consider donut with its inside part. It didn't have to be a surface. So I'm just drawing these lines to show you the three-dimensional shape. And think of it as having clay. This donut is made out of clay, which is still soft. And now you can start shaping this clay into something else. So maybe you will start yeah, maybe it's more useful to think of it in terms of it inside part as well, not just the surface. So then you start molding the outer side. You'll do actually no, you what you do is you pick an area here and you start making a kind of hole in it, but not breaking anything. So you do something like this to the donut. You start bending it in such a way that there is some kind of so this bends inside like that. Okay. You start bending it, making a hole there, and then eventually you make a coffee cup. So this hole now is that hole. Things have been stretched and squeezed, and the placeholder for the coffee here is the thing we started to shape here by pushing our fingers into this area of the clay donut. Now this transformation from the donut to the coffee cup is what topologists call a continuous transformation, because you're not breaking anything. It's continuous in the sense that you're not breaking anything. You're not taking your donut and breaking it apart. You're always either sticking things with each other or stretching things and squeezing things. So here we have two transformations, and they both will be morphisms in our category, and the composite of those morphisms is the overall process of turning a donut into a coffee cup. Okay. Right now, if I think of this discretely, sort of, if I think of my space consisting of points, I can start putting some markers for points that describe my space. Then what will happen is that these points will be mapped to further points, and they will be mapped to further points. And in this specific case, there will be a one-to-one correspondence between the points. We will not really be sticking anything in this specific example. We will be just stretching and squeezing, but never bringing two different points to the same point. And not just that, this mapping of points. So basically, if I had a marker here, let's say marker A, and on my coffee cup, I find this marker A to be there. On the other hand, I had a marker B here, and then I find that to be somewhere down here in the base. So that's the idea, right? So this is a one-to-one mapping of the points, and the idea of continuity is that if I had if I take a random continuous path connecting A and B, then these paths will never break. They will always stay continuous. So in this intermediate step, for instance, I'll have, let's say my point A is there and my point B is here. It will remain to be some sort of deformed but still continuous path. And then the same goes here, and this one will now go around here and then descend down there and then eventually connect to B. Okay. In fact, a path itself is an example. A path of connecting points itself is an example of a morphism, what in topology is called the continuous mapping. For you could take the unit interval seen as a space, so we can see it as a thread, like this. So this is now one line, so it doesn't have any thickness; it just have height. This is our number 0, number 1. All the other numbers are arranged in there continuously. And when I have a path on my space, such as on the donut, so let me copy this. I can think of this as a morphism where, let's say the start of my thread, the number 0, gets mapped to the first marker A, and then all these points here, they continuously get mapped to the points on this yellow path. And this parameterizes my path, right? Often, I mean, I can write down my paths using things called parametric equations, and this is what we'll be effectively doing here. So I can actually define a path on my donut as a morphism from this space, which we call the 0, 1 interval. So from this topological space to the torus. Any questions so far? Okay, so I gave you intuitive description of objects. These are spaces, sets equipped with some sort of notion of continuity. Morphisms are mappings of these sets which preserve continuity. So they're called continuous functions. And to describe a category now we also have to say what equivalence of paths is. So imagine that I have a shape. Let's say I've got a vase seen as a topological space, and I'm deforming it into a disk. I'm making it flat. Obviously, there are many ways of doing that, right? So I could, for instance, start by doing something like this from the top, opening it up, right? And eventually making it flat. So let's put some markers to keep track of where we are. So let's say I've got a marker there, green marker, and this green marker, maybe I'll put one there. So there, and the green marker becomes here. And then I have an orange marker at the base of my vase, and that is right there, which then becomes the center of that disk. And so I keep track of all these markers, what happens to each of them. If I have these sequence of deformations of the vase into a disk, and I have another one, so I have two paths, and this one also could have many steps in between. Then for these paths to be equivalent, it means that when I place my markers on the vase and I follow what happens to these markers in this deformation, I will get exactly the same markers for the top process as I will for the bottom one. If I get exactly the same markers on my disk, on my final disk, then I will say that this path of morphisms is equivalent to this one. And when we represent topological spaces as sets of markers, then a continuous function will become a special kind of a function. And this is just saying, as before, as in the category of sets, that this composite of functions is equal to this composite of functions. Okay, now why did we look at this example? Well, first of all, it's a very important example. It's the category of topological spaces. So let me write this down as a sentence. Equivalence of paths means that means the same end result for markers in both combined processes. So we get this way. The category of spaces. And if we are really formal about what a space is, and we take the formal definition of a topological space, then we get the category of topological spaces. Now, these topological spaces are very important. Special kinds of spaces, in fact, all of the ones I've been showing you, are called manifolds. And manifolds are the central structure in various topics in physics, including the one that studies space-time. So this is Einstein's general theory of relativity. There is a wonderful book by two authors, Stephen Hawking and George Ellis, called The Large-Scale Structure of Space-Time. I've met George Ellis, by the way, because he's actually a professor at the University of Cape Town, which is a university not far from University of Stellenbosch, where I work. And if you look at that book, I mean, the point of that book is to lay down foundations of general relativity theory, the mathematical foundations of it, and it is one of the standard books people use in that field. But if you look at the beginning of that book, it gives a very nice set theoretic introduction to manifolds. And the morphisms in that theory also play an important role, because the morphisms describe how you could possibly transform one manifold into another. The reason why it's called space-time is because you have actually not just three spatial coordinates, but you also have a fourth coordinate which describes time, the time coordinate. So these spaces are really useful as a model of space, even in physics. Now, one thing that we like to do with spaces, both in mathematics and in physics, is to sort of glue them with each other. For instance, the Klein bottle itself can be seen as a process of gluing spaces. And I want to show you how we could capture this idea of gluing using the language of the category of spaces. So we will consider one simple example. This will be how to get a donut out of a cylinder, or maybe an even simpler, yeah, maybe that example is more interesting than the other one. So let's look at that example. So let's say I've got a cylinder. And I want to make a torus out of it. Torus is a scientific name for a donut. So I can get a torus by sticking this to that side in a certain way. So let's put some markers here. So let's put a green marker and another green marker, two markers of the same color, because in the end result, they will end up being the same point. So then this becomes that. On the other hand, if I have, let's say, orange marker here, then that becomes that, and so on. So the red marker, that becomes that, and so on. So what we're really doing, we're taking the cylinder and we're stretching it out like this and turning it around and sticking the ends of it together. So this was supposed to be just the surface of the cylinder, right? And we get as a result just the surface of the torus. And we can think we can represent this process that we've just completed. We can represent this process as a morphism from the cylinder to the torus that maps these markers the way they will get transformed by this process of stretching the cylinder and then sticking it in this way. Now, I can encode the information of what will get stuck to what using two further morphisms. So let's just look at the top circle of the cylinder as the base circle, and let's think of it as just as a circle. So this has its own markers. And I can consider two morphisms. One that, so I'm just thinking about something here. Alexandra, I didn't make any mistakes, did I?
So what does the left picture do here?
No. Before we talk about the left picture, are you happy with this one?
Yeah, totally.
I think the information we gave about the markers fully captures the construction. Do you agree with that?
Yeah.
Okay, great, thanks. So now the left circle, we're going to consider as a separate space. It's just a circle. And we're going to embed the circle inside the cylinder by matching it, the top circle of the cylinder, and separately by matching the bottom part. And that also is a morphism in our category. So a morphism doesn't have to necessarily so what you can do, you can take your space, you can deform it, and then also bring some new things and attach new things to it. That is still a morphism. And so we can consider one morphism, let's call it so let's call this thing Q, and let's call this one F, which just takes the circle and attaches it to the bottom to the top of this cylinder. So like this, according to the markers as they're shown. And then let's consider another morphism, G, that does it here. Okay. It does the same thing, but attaches it to the bottom part. Okay, now let's write out these things as using just single letters. So we've got a circle here. Let's write S for that. We've got a cylinder. Let's write C for that. And we've got a torus. Let's write T for that. We've got two morphisms, F and G. And we've got a single morphism here, Q. Now, something interesting happens when I compose Q and F and compare it with the composite of Q and G. What is the composite of Q and F? The composite of Q and F will take this circle. Well, F will first put it here, and then Q will transform it into this thing, right? That's what QF will do. On the other hand, what about QG? QG will take this thing, we'll put it here, and then Q will place it again here. This is too small, but you understood what I'm saying. What do you think is the relationship between this composite QF and the composite QG, based on the illustration that we just saw?
Oh, they're equal.
They're equal. So the composite QF in both cases takes this thing and places it over there, but shrinks it a little bit as well. There we go. So they're equal. Now, when I have a cylinder, right, and when I'm making a torus out of it, in a sense, that's what I'm doing. I'm making this top circle of the cylinder equal to the bottom one by gluing it that way, right? That's my intention. When I build a torus, my intention is to take the cylinder and make those things equal. So in a sense, the fact that these two things are equal kind of encodes the information of how to build a torus out of, actually it encodes the information of what I'm trying to do, what I'm trying to build. So how we're building a torus out of a circle. And it turns out that using the morphisms, we can actually describe this construction of building a torus out of the cylinder as a construction that can be expressed purely in the language of categories. I mean, purely in the language of morphisms. So these things are equal, as we said already. And then it turns out that not just that there is additional property that this Q morphism has. And that property is that if I had some other way of deforming my cylinder, let's call it Q prime, to some shape T prime. So now I do something else to the cylinder. Maybe I squeeze everything into a single point, or I do something crazy. But in such a way that Q prime F is still equal to Q prime G. Okay, so consider any morphism Q prime from C to T prime such that Q prime composed with F equals Q prime composed with G. It turns out that no matter what this morphism is, no matter what other things we do to the cylinder, we could actually get this by first turning the cylinder into a torus and then doing some further things to the torus. So there will be some morphism from T to T prime so that this path gives me exactly this morphism. And in fact, this thing here will be unique. So if I consider any other morphism Q prime such that Q prime F equals Q prime G, then there will exist, unique, it's an abbreviation for exists unique, right? The existential symbol and the exclamation mark. There exists unique morphism H from T to T prime such that the Q prime can be obtained as the composite of H and Q. So this might be a little bit complex logical sentence for you. You might not have seen before such a process. We are going to talk a lot about these kinds of things in the future. But intuitively, what we're saying here is that if you have a way of doing something to the cylinder that achieves this part of the cylinder and that part of the cylinder to match onto each other, whatever that is, no matter what you do to the cylinder, you can always get that by first turning a cylinder into torus and then doing some further things to the torus. Now, why is this idea useful? The reason why this idea is useful is that, in fact, this can be used, this property that the Q map has, that the Q morphism has, this can be used as a definition of the torus. It will turn out that if I had some other thing, some other shape here that makes F and G equal, and that has this property that I put in the yellow area, that thing will always be something that's topologically indistinguishable from the torus. So something that you can deform back and forth continuously in a one-to-one way, back to two torus and back as well. So we can actually use this this property here, which is expressed purely in terms of morphisms of the category of spaces. We can use this property to describe the construction of a torus. And in fact, it is not just torus that we can construct this way, but all sorts of other things. We can also construct client bottle this way, but then we'll be doing the matching in a different way. We will be to get a client bottle. You'll be changing the orientation. So these markers will not be matched this way, but in a soft way. And you can even get a cylinder out of a sheet of paper by trying to glue this with that, by folding paper like this and then gluing the edges. So all these constructions that we can describe intuitively by transforming spaces can now be described just using the language of processes of these transformations between spaces. So the language of the category of spaces. Any questions at this point? So we are now introducing a new idea, so it might be a bit challenging to grasp the idea. It will be useful if you can ask me questions that could clarify the idea for you. Joseph seems to be happy. Okay. All right. It seems like this is not so challenging after all. That's good. Right. Now, what we're going to do now is to introduce a concept in a general category that will be essential for us to be able to capture these kinds of constructions using the properties like the one stated in the yellow area. And that concept is the concept of an isomorphism. So in the context of spaces, this is this idea of two objects being deformable in a one-to-one continuous way into each other. So the idea that torus and a coffee cup are basically topologically, in terms of their continuous structure, they're the same thing. So of course the metric structure is different. If you start measuring distances between markers on your torus, and you start measuring distances between markers on your coffee cup, you'll get different distances. So this transformation of turning a donut into a coffee cup does not preserve distances, but it preserves the continuous structure and doesn't stick things, so it keeps things separate. So it's a one-to-one mapping as well. And so this idea of a one-to-one mapping can be captured categorically also, like many other things. And that is the most fundamental, one of the most fundamental concepts we want to clarify, because we will be using it quite a lot in trying to define things categorically. So for instance, here I said that if I took the same yellow property, this would give me my torus back. So I could use this as a definition of the torus, but actually it will give me my torus back only up to this one-to-one continuous deformation. So only up to isomorphism. So I first need to know what an isomorphism is. And that will take us to counting. Now I'm going to go back to the category of sets and motivate that concept of an isomorphism from that category. I see I don't have any more space on my board. Let me see if I can make it. Maybe I'll extend it this way. There we go. Actually, for the purposes of publishing this later online, it's better to extend it vertically. So we looked at two categories so far. It was the category of matrices, and it was the category of spaces, of topological spaces. And now let's go back to the category of sets. where objects are sets. So you can really think of this intuitively as some collections of things. And a morphism, so if you have two sets x and y, a morphism from x to y is a function. From the set x to the set y. What about equivalences? So if I have two paths of morphisms given by f1 up to fn, and I have another one, so one is f1 up to fn, the other one is g1 up to gm, they will be equivalent exactly when the composite of functions are equivalent. And of course, in this category, well, we have to probably show that it's a category, but it's not difficult to show that. I'm going to skip over that. This category, in this category, composites of morphisms in the path will be the usual composites of functions. So it's a framework that we're familiar with.
Prof.
Yes.
It should be x to y right there on the equivalence, not x and x.
Yes, thank you. That should be y there. That's what you're saying, right?
Yes.
Thank you very much. Okay, so what is a one-to-one correspondence? And first of all, why is this useful? So this is this idea that if I have a set, let's say I've got set here with 4 elements, and I have another set with another 4 elements. One-to-one correspondence is something that gives a picture like this. In practice, let's say I've got a bunch of candies, so I've got several candies, and I have several children I want to give these candies to. And I want to make sure that everybody gets the same amount of candies, and perhaps I will be giving one to each. Right? So I will give this candy to that person, and this one to that one, 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 and this one to that one. Of course, I could also do it in a different way, but in the end, I will get something that can be represented using a diagram like this. So when I have a one-to-one correspondence, it allows me to know that the number of elements in this set is the same as the number of elements in that set. And this is actually a very fundamental idea, because even if I don't know how to count, I can still tell that two sets have the same amounts of elements just by knowing that there is a one-to-one correspondence between them. This is how Georg Cantor used to study infinity. So in set theory, there is this idea that infinite sets can have different sizes. And the idea is that you might have infinite sets, 2 of them, for which you cannot pair them this one-to-one way. And so if you cannot pair them that way, then they must have different sizes. It's a fundamental notion that is kind of at the foundations of counting. We can express this notion using functions, because when I have a diagram like this, I can immediately see 2 functions here, right? One function is turning these into mappings from left to right. And the other function is turning these into mappings from right to left. So there is this green function from left to right. So let's call this things x and y, and then this function, let's call it f. And there is a orange function. Which color did I use? Orange? Orange function reversing the process, right? It exactly reverses the process. So the orange function goes from y to x. Now these two functions, if I compose them, something interesting happens. So what will be the composite of g and f? If I first give these candies to the kids, and then I tell them, oh, I gave you something wrong. The candies are not so sweet. You need to give them back to me so I can get new candies for you. So you give these candies to the kids. That's your function f. And then you tell them to give them back to you. And that's your function g. And the result of that will be that every candy will go to its original position if they were arranged in a box or whatever. So if I apply this composite to an individual element, what will happen is the value of this will be g of f of x, and that will be the same x back, right? And the same will happen on the other side. So if I first did g and then f, I will get back a y that I started with. Now I can write these equalities of functions, or rather these computations of the values of these two functions. I can write them down using just the language of category theory. So how would I do that? I can write them down by saying that the composite GF is the same as what? And here is a question for you to make a suggestion how to answer.
1x.
That's right. Remember, 1x was the morphism. That's the composite of the empty path of morphisms. And the empty path of morphisms corresponds to doing nothing. It corresponds to taking every element of my set and keeping it there. So I'm not mapping it to something else. I'm mapping it to itself. So so these computations can be expressed this way, and the second one can be expressed this way. And so I get these two equations. And in fact, if I started with this, imagine I have something like this to start with, right? I've got two mappings, f and g, in such a way that they reverse of each other. Then, of course, I will be able to make a picture like that out of f and g. So I will have this one-to-one correspondence. So this idea of one-to-one correspondence is fully captured by a pair of maps which compose this way, that each of the composites are these identity maps, identity functions. And that brings us to this concept of an isomorphism. In a category, an isomorphism is a morphism. Let me say an isomorphism from an object x to an object y is a morphism f from x to y such that there exists a morphism g from y to x for which g composed with f equals identity of x, and f composed with g equals identity of y. Okay. Now we kind of prioritized here f over g, right? We called f an isomorphism. What about g? Will g also be an isomorphism? Well, the thing is that these equalities, they can be swapped, right? We can rearrange the order, and then for G, you will have the F making these whole, which will make G into an isomorphism as well, right? On the picture, if I have the green map for which there is a reversal orange map, then that orange map will also have a reversal. It will be the green map. So when F is an isomorphism, G will also be an isomorphism. Another interesting observation about isomorphisms is that for each F, there will be exactly one G. So if I've got a green map and I know it can be reversed, then this reversal will be unique. There's only one way to reverse, and this is something we can actually prove as a theorem in a general category. So let's sketch the proof of that. So imagine I've got F and I've got G. That brings me back to X, so that this composite is equal to the identity. So the two paths are equivalent, right? Let me rather draw it like this. So this is equivalent to this. But imagine I have a second one like that. I have also some other G prime that does the same effect. G prime that makes this path equivalent to that path, but also the other way around. So I have these, and I also have that the other way around is true. So if I have G going from Y to X, followed by F, then that is the same as that. So I have equivalences here and here. And I also know that the same is true on this side. I've got G prime, and then F. That is the same as identity of Y. How can I conclude from this that the G and the G prime are the same? So this is what I know. I know these equivalences hold in the category, and I want to conclude from this that the G and the G prime are the same. So I can take my G and I can rewrite it as G composed with the identity of Y. Why is that? Why would G be equal to G composed with the identity of Y? Let's remember what a composite is. What is a composite? A composite is something that is equivalent to a path, right? So I've got my G path from Y to X. And then I've got here, I've got the identity of Y, and I've got G as well. But now this thing, the identity, is equivalent to the empty path, right? So the identity is equivalent to the empty path. And by the congruence property, the path. So let me draw the empty path by a dashed arrow. So this is the empty path. And remember the congruence property, how it works. If I've got equivalence in the middle and I extend, so I've got equivalence of two paths and I extend each of these on either side, then the resulting paths will still be equivalent. So this path has to be equivalent to that path, right? But because this is the empty path, this longer path is just the G. So that's how I get that these are equivalent. And if they're equivalent, then they must be equal because, as we already know, the composite is the unique single morphism path that is equivalent to my path. So I can write G as G composed with identity, and then I can continue this. I can write this as G composed with, so what is identity? Identity is equivalent to FG. So G composed with F, and actually I'm going to use this one. G composed with F composed with G prime. And now I claim that, in fact, this is equivalent to first composing G and F, and then composing that with G prime. And let's see why that is the case. So I've got my G prime here, composed with F, right? And then further composed with G prime. But first I'm doing the G prime F composite. So I'm forming this single morphism that is my G. Sorry, actually this is the G, not the G prime. What am I doing here? I actually want to do this other way around, right? So I want to take this to be G. So this is what I'm getting here. This is my G composed with F, right? So this is equivalent to that by definition of the composite. By definition of this composite, it's the morphism that's equivalent to this path, right? And then now I'm composing this with that. So I'm now considering this path and forming a single morphism that's equivalent to that. So there we go, right? And that's going to give me the right-hand side of the equality. So this is G composed with F composed with G prime. But I also have the left-hand side of it, which I can draw in the same space. So in the left-hand side, which is this side, I first compose F and G prime together. So I'll have this F composed with G prime, and I've got that equivalence there. And then I compose that with G composed with F composed with G prime, and I've got that equivalence there. Now remember I claimed that these two things are equal to each other. We can now see from the diagram that they are. For take my left side of the equality. This is equivalent to that, right? By congruence, because this is equivalent to this, by congruence, this path is equivalent to that path. By transitivity, this will be equivalent to that path. Again, by congruence, this path will be equivalent to this path. By transitivity, this then will be equivalent to this. And then again, by transitivity, this top one will be equivalent to the bottom one. But because they're both single morphism paths, by equality axiom, they will be equal. Fantastic. Then I can continue my calculation. I've got GF here. What is GF? GF is identity of X, right? So I can write here identity of X composed with G prime. And we're using exactly the same argument as I did for this equality. I can get that to equal G prime, in the end proving that G equals G prime. So if an F has two ways of reversing it, these two reversals, G and G prime, will always be equal if we're in a category. And to prove that, we used two properties that kind of derived along the way. If you were observant to what we did, to establish this equality, we actually didn't need to know what is G. This equality, this proof we gave here, actually works for arbitrary G. The same way this equality works for arbitrary G prime, and the same way this equality holds for arbitrary triple G F G prime. And this brings us to the standard definition of a category, which we're going to examine in the next lecture, where I can have a collection of objects and morphisms. I can have a way of composing any two consecutive morphisms so that the composition is associative, and these rules hold, which are called the identity laws, and this is enough for me to have a category. So I can derive all the equivalences just from this information, and this is very useful because when proving something, we now have to give much less data. Of course, giving equivalences of arbitrary pairs of paths is much more data than just giving for every two consecutive morphisms a third one.